Hello, dear students. Good evening to all. Sorry for being late. I just have to complete my previous class. It took some few minutes to complete that. That's why I'm being a little bit late today. But anyway, can you all able to hear me and see me and my screen? If I'm visible and audible to all of you, just give me a response in the chat box. Am I visible and audible to all of you? Hello? Students, class 12 students, am I visible and audible to all? Can anyone let me know in the chat box? Yes or no? Ray, can you able to see me? Hello. Swapna, Navya, Santosh. Can you guys hear me? Janani, Veera. Yes. Thank you, Bhavya, for your response. Yes, let's start with the class today. Fine. So we are in P block elements lesson, right? So, and in this group 15 has got over, and yesterday we have started group 16. Basic concepts, physical properties of group 16 got over, and we are in the chemical properties of group 16, right? So the chemical reactions of group 16 elements were the reaction with hydrogen, reaction with oxygen, and the reaction with halogen. So among these three, reaction with hydrogen was discussed yesterday. And today, we are going to see the reaction with oxygen and halogen. So moving on to the first, which is the reaction with oxygen. So when group 16 elements react with oxygen, they form two different types of oxides. Okay. One is EO2 type and the other one is EO3 type, where E is the group 16 elements. Okay. EO3 type of oxides are more acidic. This oxide is more acidic compared to the EO2 type. Why? Because the oxidation state of the element in EO3 is +6 and the oxidation state of EO2 element is +4. The one which is having the higher, more positive oxidation state will act as a Lewis acid, right? So that is more electron deficient in nature. So it is a Lewis acid. So that's why that is more acidic than EO2 type of oxides. Okay. So these are the EO2 type of oxides. So in this first O3, you can see that element is oxygen and it is bonded with two more oxygen. So that's why it is forming EO2, that is O3. And here sulfur is the element and O2. Okay, sulfur dioxide, selenium dioxide, and tellurium dioxides. So among these four oxides of type EO2, the first two oxides are gases. Okay, and the remaining two oxides are solids. So this is the physical nature of the EO2 type of oxides. Got it? So the first two is gas and the remaining two is solid. Now the symbol of all the elements of group 16 are oxygen, sulfur, selenium, and tellurium. On moving down the group, we all know that the stability of the higher oxidation state decreases. Stability of the higher oxidation state decreases on moving down the group. The reason is due to inert pair effect, right? So the lower oxidation state stability only increases. Lower oxidation state stability only increases. So comparing +6 and +4 is more stable for the last element, that is for tellurium. Okay. Now in all these oxides, you can see the element is in +4 oxidation state. Now tellurium in +4 oxidation state is more stable. Okay. And the reducing character decreases. Since the tellurium oxide is more stable, it cannot get reduced so easily. So the reducing nature decreases when you go from O3 to TO2. Got it? So what happens if reducing nature decreases, oxidizing nature increases? No, oxidizing nature increases. So tellurium dioxide is an oxidizing agent, while sulfur dioxide is a reducing agent. Okay. Since the oxidation state of tellurium and sulfur is +4 in these two compounds. So who is the reducing agent? The reducing agent is the one who gets oxidized. Reducing agent is the one who loses its electron to the one to which is getting reacted. It loses. Sulfur dioxide is a reducing agent, means sulfur dioxide will give its electron to the species to which it is reacting. Okay. So that is called as reducing agent. So the reducing agent is the one who gets oxidized by reducing themselves, and the sulfur can go from +4 to +6. So it is getting oxidized by losing its 2 electrons, while tellurium cannot go from +4 to +6. So it can exist only in +4 because of inert pair effect. So tellurium cannot give its 2 electrons to get converted to +6. This is not possible. If it cannot loses its electron, it cannot act as a reducing agent. So that's why tellurium dioxide is not a reducing agent, it is an oxidizing agent. Got it? Now, both the oxides, EO2 or EO3, both the oxides are acidic oxides only. This is little bit more acidic than the other one, but both are acidic only. Both are having positive oxidation state, no? So both are acidic in nature. Got it? So coming to the next. Hello Sandeep, good evening. You have joined so earlier today. Happy for you. I'm very so happy for you. Good evening. So you don't have study hard today or what in your school? Okay, anyway. Okay. Okay. You don't have study hard. Oh, no. Fine. Yes. So Sandeep, we are discussing the reactions of group 16 elements. Okay. So far I have completed. Yesterday we have completed reaction with hydrogen, and today I have completed reaction with oxygen, and now we are all of us are moving on to reaction with halogen. Okay. So students, when the group 16 element react with halogen, it forms 3 different types of halides, and the formula you can see it on the screen. EX6, EX4, EX2. X is the halogen. Who are the halogens? Fluorine, chlorine, bromine, iodine. And what is that E? E is the group 16 element. Okay. And talking about the stability of these halides, the fluorine containing compounds are more stable. Fluorine containing compounds, you can see the order. Fluorine containing compound is more stable than the chlorine, than bromine, than iodine. Okay. Now coming to the EX type. EX means, EX6 means hexahalide, right? 6 halogens are there. So it is called as hexahalide. So among the hexahalides, it can be OF6 and OF4, OF2. Among this halide, now we are talking about the hexahalide. So among the hexahalide, the hexafluorides are the most stable halide. Hexafluoride. If I am comparing the element with okay, let me take SF6. Not SF, it is OF6. OF6 is not possible. SCF6 and TF6. Okay. Now among these 3, or I can say SF6, SCL6, SBR6. Among these 3, if you see, the hexafluoride, fluorine containing compound is more stable than the chlorine and bromine containing compound because of this stability. Okay, so hexafluorides are gaseous in nature. They are gases. SF6 is a gas. So here is the structure. It is having octahedral structure, right? So 4 atoms at the corners and 1 above and 1 below. So all the geometry information we have already discussed in coordination compounds lesson, no? So it is an octahedral geometry. If the geometry is octahedral, what is the hybridization? Can anyone tell me the hybridization for the octahedral compounds? Can anyone tell me the geometry, hybridization for octahedral compound? Not even a single student knows the answer for this. What is the hybridization of an octahedral? Yeah, very good, Navya. It is sp3. Yes, good, Veera. It is sp3d2. sp3d2. Good. Good, Santosh. It is sp3d2 hybridized system with the octahedral geometry. And this SF6 is exceptionally stable due to steric reason. It is exceptionally stable due to steric reason. Got it? Now coming to the next type, EX4 type. So three compounds are forming, three elements are forming this type: sulfur, selenium, and tellurium. These three elements are forming SF4 compounds, EX4 compounds. Sorry. Now among these three, SF4 is gas. SF4 is a gas. SF4 is a gas, and selenium tetrafluoride is a liquid, and the last one, tellurium compound, is a solid. Okay, this is the physical state of the tetrafluorides of group 16. And talking about the shape of EX4 type or the geometry of EX4 type, it is looking like this. What is this? It is trigonal bipyramidal geometry. The geometry is trigonal bipyramidal. If you are considering the lone pair also, then it is geometry. And if you are seeing the structure without lone pair, then it is shape. Okay. So the geometry is trigonal bipyramidal. And if we are not considering that lone pair of electron, and if you are seeing only the 4 bond pairs, then you will end up with shape. The shape will be a seesaw. The shape is seesaw. This type of concept, the seesaw shape and the trigonal bipyramidal geometry, all these concepts you might have studied in your chemical bonding lesson of class 11. Okay. So there are 2 things. If a compound contains lone pair, then shape and geometry would be different for that compound. To find out the shape, don't consider the lone pair. To find out the geometry, consider the lone pair. Okay. Now on considering the lone pair, I will get trigonal bipyramidal. Shape is seesaw. If these 2 halides come together, it will go up. If this contracts, it will go like this. Okay. It is seesaw kind of system with sp3 dehybridization. Since only 5 bonds are there, it is sp3 dehybridization. Okay. So this is about these 2 types. Then coming to the last type, which is EX2, the example is like this. Element is forming 2 bonds with the halogen and 2 lone pairs are there. Since all the group 16 elements are having 6 valence electron, only 2 valence electron has formed the bond. Remaining 4 electrons are there, no? So they are located as 2 lone pairs. Now, what is the hybridization of the element in EX2 type? Can anyone find the hybridization of element in EX2? So how to find out the hybridization? There is one formula to find out the hybridization, right? It is steric number. Steric number is equal to number of sigma bonds plus number of lone pairs. Okay. So how many sigma bonds we have? We have 2 sigma bonds and 2 lone pairs we have. So the answer is 4. If the steric number is equal to 4, then the hybridization is sp3. Okay. If the steric number is 5, it is sp3d. If the steric number is 6, it is sp3d2. So this concept you might have studied in your chemical bonding lesson. So here I'm having 2 lone pair and 2 bond pair, that is 2 sigma bond. So I'm getting 4 as the steric number. So 4 orbitals, 1s and 3p will intermix to give sp3 hybridization. So all the sp3 hybridization containing compounds will have tetrahedral geometry, right? So the geometry is tetrahedral and the hybridization is sp3. Got it? Now, all the elements of group 16 except oxygen form dichlorides and dibromides. All the elements except oxygen will form dichlorides and dibromides. Okay. So the example you can see. Except oxygen, they form dichloride. Oxygen will not form dichloride and dibromide. Only OF2 is possible. OCl2 and OBr2, it is not possible. Why it is not possible? Due to the repulsion between the 2 chlorine atom and the 2 bromine atom. Okay. So the repulsion occurs between them. So because of that, the compound becomes unstable. So they are not existing. Only OF2 is existing for EX2 type. Got it? Now they are able to form the dimers also. They are able to form the dimers. All the compounds except oxygen, they can form dimers. Dimers means 2 times you have to do. Multiply by 2. If it is SF, you will have S2F2. So S2Cl2, S2Br2, this kind of system you will have. They are the dimers. Other than oxygen, all others are forming dimers. Got it? And this dimeric compounds undergo disproportionation reaction. You see, I have taken Se2Cl2. So here the oxidation state of selenium is 2x minus 2 equal to 0 and x is equal to plus 1. The oxidation state of selenium is plus 1 in the reactant side. In the product side, you see it is plus 4 in one of the product and in the other product it is 0. It is an element, right? It is not bonded with any other atom, so it is 0. So in one compound, the oxidation state is going from plus 1 to plus 4. That is oxidation. And in the other compound, the oxidation state is moving from plus 1 to 0. If it is moving from plus 1 to 0, it is called as reduction. Okay. Increase in the positive number or increase in the positive charge leads to oxidation. Decrease in the positive charge is reduction. So the same element is getting oxidized as well as getting reduced. So those reactions are called as disproportionation reactions. So the dimeric compounds of group 16 elements other than oxygen are able to undergo this disproportionation redox reaction. Okay. So that's all about the chemical properties of group 16. Now the last topic for group 16 compounds is the anomalous behavior of oxygen. What is anomalous? Unique behavior, right? So like nitrogen, we are going to study for oxygen also. The same reason. So due to the unique behavior of oxygen is due to small size, high electronegativity, high ionization energy, and absence of d orbital. The same 4 reasons which we have discussed for nitrogen is applied here. Okay, so oxygen will behave differently. In the last reaction also we have seen, no, it will not form dichlorides and dibromides, whereas other elements will form dichlorides and dibromides. So it will behave, oxygen will behave differently in many things. It is due to these 4 reasons. Okay, same reason which I have discussed with the nitrogen. And they are able to form hydrogen bonding like NH3. Like nitrogen formed hydrogen bonding, oxygen can also form the hydrogen bond. You can see in the water molecule. So this 2 water molecules are given to you. The oxygen of one molecule is forming the hydrogen bond with the hydrogen of the other molecule. Okay. So this hydrogen bonding is very, very strong. So why it is very, very strong? Because of the very small size of the oxygen. Okay. Because of the very, very small size of the oxygen, usually small size atom will form the strong bond, no? So due to its small size and high electronegativity, it can able to form the strong hydrogen bonding. But whereas sulfur, selenium, tellurium, if you see, they will not form a strong hydrogen bond because you see here, H2S I have taken for you. So here the size of the sulfur is large and the electronegativity of sulfur is very less. Okay. If these two are the case, then the hydrogen bonding formed by that particular element will not be strong. So there is no formation of hydrogen bonding in H2S. Okay, due to the large size and less electronegativity of sulfur, it will not enable the hydrogen bonding. Got it? So only oxygen is having that capacity to form the hydrogen bonding. So that is another unique behavior of oxygen. Got it? Now coming to the next behavior, it can able to form p pi multiple bond like nitrogen has formed. But in case of nitrogen, there are 2 pi bonds formed by nitrogen. But oxygen, if you see, if I take oxygen molecule, there's only 2 bonds between oxygen, right? So one is sigma bond and the other one is pi bond. So only one pi bond is formed by the side base overlapping of p orbital. One p orbital of both the oxygen. So this is one oxygen and this is the other oxygen. So one p orbital of both oxygen overlaps in the sidewise manner to give the pi bond. Okay. Since the size of the oxygen is very, very small, they can overlap so easily to form the multiple bonds. The small size makes the formation of multiple bond easier. Okay. And the maximum covalency of oxygen is 3. Maximum covalency of oxygen is 3. At the maximum, oxygen can form only 3 bonds. In case of H3O plus, you can see that oxygen can form 3 bonds. Okay. So it cannot expand its covalency more than 3. So what is the reason for that? Because of the absence of d orbital. Okay. Since no d orbitals are present, an atom cannot come and form the bond with, or an atom cannot expand. This oxygen cannot expand its covalency more than 3 due to the empty d orbital. Got it? So it is 3. Maximum is 3. So in H3O plus, you can see it is 3 bond. H2O, mostly it will, in most of the cases, it forms only 2 only. H2O, OF2, O2. In all the cases, you can see that oxygen can form only 2 bond. Okay. Maximum is 3 in H3O plus. So that is the unique nature of oxygen. Now there's a question for you. Why H2O is a liquid but H2S is a gas? Can anyone try for this? H2O is a liquid but H2S is a hydrogen sulfide is a gas. Okay, it's a foul smelling gas. No, H2S is a foul smelling gas. But water is a liquid. What is the reason for that? Simple and easy reason only. Just think for it. Why H2O is a liquid and H2S is a gas? Any idea? No idea? At least class 12 students can give a try, no? So I am not expecting you to give the correct answer. At least you can try, right? Don't get scared. Or don't get hesitate. So H2O is a liquid because of the formation of hydrogen bonding. Hydrogen bonding is the intermolecular force which is existing between two H2O molecules. Okay, but in H2S, there is no such bonding. So it cannot form the bond and it exists as gas. Got it? So the same reason. Van der Waals forces are the very weakest force than hydrogen bonding. In H2S, there is only Van der Waals force existing. But in case of water, we have hydrogen bonding. Van der Waals force is the weakest force among all. So it will exist as gas. Van der Waals force mostly exists in gases only. So H2S is a gas and H2O is a liquid. Got it? So this is about the group 16 elements. Let me summarize this. So firstly, we have seen the electronic configuration, which is NS2, NP4, right? Sorry for this. It is NP4. And here are the elements and its configuration to you on the screen. And coming to the trend, atomic radius increases on moving down the group. Then ionization energy decreases on moving down the group. Electronegativity also decreases on moving down the group. Electron gain enthalpy also decreases on moving down the group. Okay. Metallic nature increases. Atomic size and metallic nature, they are directly proportional. And the boiling point, it is also directly proportional with the atomic radius. It also increases because the molecular mass increases. And stability of the higher oxidation state, that is +6, also decreases due to inert pair effect. So talking about the common oxidation state of group 16, it is +4 and +6, as I have already discussed. And when the group 16 elements are reacting with hydrogen, they form hydrates of type H2E. And when they are reacting with oxygen, EO2, EO3 type of oxides are formed. And when they are reacting with halogen, 3 different types of halides are formed. Got it? So this is the very short summary of group 16 elements. And all the compounds of group 16s are again deleted for all of you from this year onwards. So we are not going to study the compounds of group 16. Okay. Now I am jumping into group 17 elements, which are otherwise called as halogen family. Okay. So do any of you have any doubt from group 15 and 16? Shall we move on with the group 17? Okay, I'll move on with group 17. So in group 17, introduction, physical properties, chemical properties, and anomalous behavior of fluorine. These 4 topics are again going to be discussed under this group also. So coming to the introductory part, halogens. Halogens. So the name is actually halogens. Why it is called as halogens? Halo means salt, genes means bond. Actually, they are the salt producers. Halogens are the salt producers. That's why we are calling them as halogens. Okay. So who are the very important halogens? The first halogen is fluorine. Next is chlorine. Third one is bromine. And the fourth one is iodine. You can see fluorine is a gas. Chlorine and bromine, they are liquid. Iodine is a solid. And one more halogen is also there, which is astatine. Okay. The last radioactive halogen is tennessine. Astatine and tennessine are radioactive in nature. Okay. Tennessine is more radioactive than astatine. Now, talking about the occurrence, so let me go with fluorine first. So, fluorine is existing in fluorspar ore, having formula CaF2. Okay. And also in fluoroapatite ore, and it is also there in cryolite. Na3AlF6 is cryolite. This is very important. Okay. Name and the formulas are very, very important. And it is also existing in the soil. Fluorine is there in the soil. And in animal bones and teeth, you can find this fluorine. Okay. In animal bones and teeth, fluorine is there. So this is the occurrence of fluorine. So all the name of the ores you study and all the occurrence you study. Now coming to the occurrence of chlorine, bromine and iodine, the major component is the seawater. Okay, most of the chlorine, bromine, iodine you can see in the seawater in the form of KCl, NaCl, sodium. All these are salts, right? Potassium chloride, sodium chloride, potassium bromide, sodium bromide, potassium iodide, sodium iodide. So potassium, sodium salts. And magnesium chloride, calcium chloride. So all the magnesium and calcium ions are also forming the salt with the bromine and iodine and chlorine. Okay. And one double salt is also there, KCl, MgCl2, 6H2O. So it is also the thing. So these are the occurrence of chlorine, bromine and iodine. In all these compounds, you can see this 3 ions. Okay. Now coming to the next topic, which is the physical properties of halogen. Usually we discuss the atomic radius. No, the same thing is going to be discussed here also. So who are the elements? Fluorine. Fluorine atomic number is 9. Atomic mass is 19. Electronic configuration, you see, it is NS2 NP5. Electronic configuration for group 17 is NS2 NP5. For chlorine, 3s2 3p5. For bromine, d orbital is coming into existence. So 3d10, 4s2 4p5. Iodine, 4d orbitals are coming, and for astatine 4f as well as 5d, and for tennessine 5f and 6d. So astatine and tennessine, as you can see, they are radioactive in nature. The radioactive activity symbol is given there, no? So those two are radioactive in nature. Got it? Now the electronic configuration is discussed to you in detail. The configuration, as I have told you, it is NS2 NP5. That is 7 electrons are there in the outermost shell. 7 electrons are there in the outermost shell. This is the nucleus, and 2 electrons are there in the first shell. 8 electrons has to be occupied by the second shell, but only 7 electrons will be there in the valence shell. Okay. And for bromine and iodine, you can see the d orbitals are filled. D orbitals are filled. For chlorine, d orbitals will be there, but it will be empty. And for fluorine, no d orbital. Okay, absence of d orbital. So this is about the electronic configuration. And talking about the radius, as we all know, atomic radius increases on moving down the group. Okay, so the covalent radius also increases, ionic radius also increases on moving down the group. The same trend which we have been studying for the other groups. Got it? Covalent and ionic radius increases on moving down the group. So there is no exceptions in this. Okay, just you have to see the study the trend. And coming to the next physical property, that is ionization energy. As the size increases, you can see the ionization energy value is getting decreased. Why? Because they are inversely proportional. Atomic size is inversely proportional to ionization energy. So that's why it is decreasing. Okay. So all these have been discussed previously. So that's why I'm going fast. I hope you all can understand. So ionization energy decreases because on moving down the group, the distance between the nucleus and the outermost electron increases. So the attraction becomes very less. So we can remove the outermost electron easily from iodine. So very less amount of energy is enough to remove the electron from iodine compared to fluorine. So that's why the energy decreases on moving down the group from chlorine to iodine. Okay. Now coming to the third next physical property, that is electron gain enthalpy. As the covalent radius increases, electron gain enthalpy value is becoming less negative. It is becoming less negative. You can see here, it is becoming less negative from 333. Here there is an exception that I will tell you in the next slide. But here and here you see, it is going very less negative from 333 to 296. Okay. But among fluorine and chlorine, there is an exception. So chlorine is having the more negative value. Actually, it should be less negative than fluorine. But chlorine is having more negative value compared to fluorine. Okay, that is an exception. You have to note it down. So what is the reason for that value? Why chlorine is having more negative? Why it is following that exception? Why is the electron gain enthalpy of chlorine is more negative than fluorine? Very simple reason. Just see the diagram. Just see the diagram. This is fluorine. Okay, fluorine is having 7 valence electron. And what is electron gain enthalpy? Adding 1 electron to the system, right? So that is electron gain enthalpy. Amount of energy released from the atom when an electron is added to that atom. So to this fluorine, we are adding 1 electron. And this is chlorine. And here also, we are adding 1 electron. But the size of the chlorine is little bit bigger than fluorine. So what happens? So if this is the last electron enters into the p orbital, right? Because it is ns2 np5, right? So np. So in np orbital, how many electrons we are having? 5 electrons, and the last electron which I am adding will fall into the np orbital. So the shape of p orbital is dumbbell. This is 2p. 2p is there for fluorine, and for chlorine, the outer orbital is 3p, right? 3p orbital will be little bit bigger than fluorine. 3p orbital is bigger than 2p orbital. So if I'm adding electron from outside to this 2p orbital, you see here, the space is very less. Already electrons are there, electron density is there. Now I am adding one more electron. So what is going to happen? Electron repulsion will occur. So the energy of the system rises. If the energy of the system rises, then it leads to the less stable condition, right? Energy and stability are inversely proportional. If energy is more, stability is very less. Got it? Now for chlorine, the size of the orbital is little bit bigger than fluorine. But the same 5 electrons are going to be there for 3p orbital also. If I am adding one electron from outside, I can spend very less amount of energy to add this electron, and the electron repulsion, that is going to be very less only. Okay, so that's why we can able to add the electron in chlorine so easily compared to fluorine. Okay, if I'm able to add the electron easily to a system, then the system will have more negative electron gain enthalpy value. Okay, more negative electron gain enthalpy value says that we can able to add the electron to an atom easily. Got it? So that's why this exception is arising because of the repulsion property. Because of the repulsion property, the order is just inversed. Like oxygen and sulfur, the same reason is followed here also for fluorine and chlorine. I hope this is clear to all of you. Am I right? If you can able to follow this, just put yes in the chat box. If you can able to follow the class, just type yes in the chat box, or if you're having any doubt, just ask me. Swapna, Sandeep, who else is there? Navya, Bhavya, Santosh. Are you all listening? Can you all able to follow? Shall I go with the next physical property? Say yes or no. Okay, Sandeep. Thank you so much. The next property is electronegativity. Electronegativity. So we all know that electronegativity. Sujan. Thank you so much, Sujan. You have joined late or what? I didn't see you while starting the class. Okay. Fine. So the electronegativity decreases on moving down the group. Okay. We all know that fluorine is the most electronegative element in the periodic table. So you see the value, it is 4. It is the highest value given. Okay. By Pauling in his electronegativity scale. So it is the first most electronegative element in the whole periodic table. So as the size increases, electronegativity decreases. Got it? So the same trend in electronegativity, we don't have any exceptions. So now I will move on to the boiling point, melting point, and density for fluorine, chlorine, bromine, and iodine. So we all know that atomic number increases on moving down the group. If atomic number increases, atomic mass also increases. Okay. If mass increases, melting point and boiling point, they will also increase. You don't have to memorize all these values. Just learn the trend alone. Okay. If the molecular mass increases, then the melting point and boiling point will also increase. Got it? If in the exam, if you're getting question like this, which among the following is the correct order of boiling point for the halogens? Like this, they are asking you one question and giving you orders like this. So fluorine, chlorine, bromine, and iodine. So what you have to do? You have to choose the correct answer, right? So fluorine, chlorine, bromine, and iodine. So this is the correct order. This is the correct order for boiling point. So this is how you are going to answer in the exam. They are not going to ask you the values and all. So you don't have to worry. And if the mass increases, density also increases because density is equal to mass by volume. Mass by volume. So mass and density, they are directly proportional. If mass increases, density also increases. And talking about the last property, that is bond dissociation energy, you see the bond dissociation energy. It is decreasing from bromine to iodine. Okay. But first you see, first it is 158 for fluorine. Then it increases. Then it decreases. So why there is an exception? First increasing, then it decreasing. So there is an exception. First of all, what is bond dissociation energy? Energy required to break the bond. So this is the bond between two fluorine. If I want to break this bond, I have to supply some energy, and that energy is 158.8. Right? So that energy is following an irregular trend for this halogen. So why? What is the reason for this irregular trend for bond dissociation enthalpy of halogens? Or why does the bond dissociation enthalpy of fluorine molecule is less than that of chlorine? Bond dissociation energy is very less means what is the meaning? We can break the bond so easily. That is the meaning, right? So we can able to break the FF bond so easily compared to CCl bond. CCl bond is strong. That is the meaning. Okay. So why? What could be the reason? So here is the structure of fluorine, and the FF bond energy is 158. And this is the structure of chlorine, and 242 is the bond energy of chlorine. Ideally, fluorine should have the highest value. Okay. Theoretically, fluorine only should have the highest value because the size is very small. It used to form the strong bond. Small size atom used to form the strong bond. So the energy required to break the strong bond should be more. Okay. That is for fluorine only it should be more. But in reality, we are observing the opposite order. What we are observing? We are observing the high value for chlorine. It is due to the high electron-electron repulsion among the lone pairs in small-sized fluorine molecule. So in case of fluorine molecule, since the bond length is very small, we all know that each halogen will have 3 lone pair of electrons, right? Each atom will have 3 lone pair of electrons. Now this is the lone pair repulsion in case of F2. Now coming to Cl2, the bond length will be little bit bigger, no? The length is very high, very large. So these are the 2 lone pairs of chlorine. 3 lone pairs of chlorine atom. Now if you see here, this is the lone pair repulsion. So in case of fluorine, since both the lone pairs are very closer to each other, lone pair repulsion is very high. We all know that. 2 lone pairs cannot come in contact so easily. They will repel each other, and that repulsion is more. So since they are very closer to each other, they try to keep them very far apart. So because of this, the fluorine bond is getting weakened. Fluorine bond weakens. So what happens because of that? Bond strength decreases, no? So that's why this fluorine bond is breaking down so easily with very less amount of energy. And coming to chlorine, the distance between 2 lone pairs is very large. Lone pair repulsion will be very less. So this bond is strong. Cl-Cl bond is strong. So that's why we need to supply more amount of energy to break this bond compared to fluorine. Got it? High electron repulsion, which weakens the bond in fluorine molecule. That is the reason. Clear for all? Shall we move on with the chemical properties? So that's all about the physical properties. Now let us move on to chemical properties of halogens. So the first is the oxidation state. You all know. And halogen can have 3 different excited states. 3 excited states are possible. Okay. So it can exist in +1 oxidation state, +3, +5 and +7. So 4 different oxidation states are possible for halogens. But the higher oxidation state of fluorine, since it doesn't have d orbital, it can be -1. Fluorine is the most electronegative element in the periodic table. It always gains the electron. It never loses its electron. So since it always gains the electron, it will always have -1 state. It will not have positive oxidation state in any of its compounds. Got it? Now the higher oxidation state of chlorine, bromine and iodine, they are, when they are bonded with fluorine or oxygen, that is in case of interhalogen compounds and oxo acids, if chlorine is bonded with fluorine, then ClF3 kind of ClF3 kind of molecules are formed, no? So these compounds are called as interhalogen compounds. When chlorine is bonded with oxygen, ClO minus, ClO2 minus. So these are basically the oxo acids. Oxo acids. Got it? In those cases, they form +4 +5 oxidation state. And +4 +5 oxidation state of chlorine and bromine is observed in oxides and oxo acids of chlorine and bromine. Got it? So this is the thing, the very important point you have to notice. Fluorine can exist only in -1 state. Okay, the remaining parts we can discuss in the upcoming slides. I will move on to the chemical reactivity now. Talking about the reactivity of all these halogen, it decreases on moving down the group. Means who is more reactive? Fluorine is more reactive. In organic chemistry, you might have studied that fluorine containing reaction will be highly exothermic. Even the test tube or the beaker in which you are doing the reaction will get burst out. So it is that much highly exothermic. Okay, it is very reactive, highly reactive. So in most of the reaction, we will not use fluorine since it is highly exothermic in nature. And iodine is just the opposite of it. Very least reactive, and the reaction with the iodine is very, very slow. Okay, so the reactivity decreases on moving down the group. And talking about the oxidizing nature of all these compounds, the small sized halogen, when it takes one electron, it is attaining the noble gas configuration. Accepting the electron nature is called as oxidizing nature, right? So if a halogen accepting an electron, then halogen is the oxidizing agent. So we are going to study about that nature. All the halogens are highly oxidizing in nature because on gaining one electron, they are attaining the noble gas electronic configuration, which is highly stable. So that's why most of them are oxidizing in most of the compounds. Got it? Now it is related with electrode potential values. In the exams, they will not ask you to write the electrode potential value, so you don't have to memorize the values. You just read the trend alone. The compound which is having the highest electrode potential value will be more oxidizing in nature. Now among these 4 values, you see which is having the highest value, E0 value, fluorine. So fluorine is highly oxidizing in nature. Fluorine can gain the electrons more easily, more effectively compared to the other elements. Okay. So the oxidizing nature of fluorine is very, very high. If fluorine is reacting with chlorine, bromine and iodine here, it can take electron from chlorine, bromine as well as from iodine. It can react with all other 3 halogen. But if chlorine is reacting with halogen, that other halogen can be bromine and iodine. It cannot be fluorine. Why? Fluorine is highly oxidizing. So chlorine cannot react with fluorine. It can react with only its lower members, that is bromine and iodine. And bromine, if you take, bromine can react only with iodine. It cannot react with chlorine or fluorine. Okay. So this is about the oxidizing nature. And here you just take down this relation. Compound which is having the highest E0 value will be more oxidizing in nature. Got it? Now next I will go with the chemical reactions of halogens. So it can react with hydrogen, it can react with oxygen, it can react with metals, and it can react with halogens. Okay, H2, O2, metals, and halogens, X2. With all these reagents, it can react. So let me start with hydrogen. Okay, so first is the reaction with hydrogen. If the halogens react with hydrogen, okay, if any of these halogens react with hydrogen, the reactivity towards hydrogen is more for fluorine. You see the arrow mark, it is going from bottom to top. No, the reactivity is very high for fluorine with hydrogen. So HF is formed more easily compared to HCl, HBr and HI. Okay. So you see the bond length keeps on increasing. Bond length increases and HF is, fluorine is more reactive towards hydrogen since it is exothermic. As I have told you, the reactivity is very high for fluorine. Got it? They are forming HX. They are forming hydrates of formula HX. Now talking about HF, this bond length for HF is very, very small. If the bond length is very small, bond strength is very high. So it is very difficult to break that bond. Okay. So what you have to do, you have to supply more amount of energy. More amount of energy. You have to supply more bond dissociation energy. Okay. So the bond dissociation energy will be very, very high. Then only you can break that HF bond and you can get H plus and F minus. Sorry for this background noise, which is getting caused by this dogs. Okay. Sorry for it. Just bear with me. I hope you will adjust. Okay. Yeah. Now it's fine. Okay. Okay. Coming to the class. So the HF bond is very difficult to break. So I have to supply more amount of energy to get H plus and F minus. So only if complete dissociation of H plus and the anion occurs, we call them as strong acid, right? But here the formation of H plus and F minus is very difficult since the bond is very strong. So HF is a weak acid. HF is a weak acid. But in contrast to HF, if I take HI, the bond length is very large. So I can break the bond so easily because of the large bond length. So very less amount of energy is enough to break that bond. Okay, it will become H plus and I minus so easily. So it is a stronger acid. So the strong acid is HI and weak acid is HF. And the reason for these two phrases you should know. The reason is nothing but the bond energy. Okay. Then talking about the properties of this HX, talking about the properties of this hydrogen halides, HF, you can see HF till HI, the bond length increases. Okay. Bond energy decreases. Here it increases and here it decreases. You all know the reason, right? And pKa, you see, it is going more negative. pKa is inversely proportional to acidity. The compound which is having the highest pKa value will be less acidic in nature. So HF is having the highest pKa value. So that's why it is the least acidic compound. In the previous slide, just now we have seen, no, it is a weaker acid. Got it? Now, melting point and boiling point, as you can see, it increases. There is some exception here, but it is increasing. Okay. This is about the properties. Now coming to the reactivity with oxygen, it is already 4:55. Okay. I think today will be the last class for you because from Monday onwards you are all having exams, right? Okay. Shall I continue with the oxygen? We have 3 more reactions. Okay. So I'll stop the class here. So we will discuss the reaction towards oxygen in the next class. Okay. So let me stop here. It is already time. You have to go for the next class, right? So I'll stop here. So what we have discussed today? So we have discussed group 16. We have discussed group 16 and group 17 till chemical properties. Got it? So remaining thing we will try to cover it in the next class if you are getting. Okay, students. Thank you so much for listening to the class. If you're having any doubt, you can ask. Do any of you have any doubt? No doubt? Okay then. Okay then. See you all in the next class. Take care. Bye-bye.